listen-only mode.
Good morning, everyone. My name is Robert Scott, and I'm the chair of BAYWORK Staff Preparedness Subcommittee, and I will be your moderator for today. I'd like to welcome you to our webinar, Integrating Ferrate into U.S. Water Treatment Practice, sponsored by BAYWORK. BAYWORK is a consortium of Bay Area water and wastewater utilities working together to ensure that we will have reliable workforce needed to serve our customers and protect the environment. Before we get started, I'd like to go over a few items so you'll know how to participate in today's event. We've taken a screenshot. Of the attendee interface. You should see a control panel in your upper right corner of your screen. GoToWebinar will automatically default to your computer's speaker system. If you would prefer to join over the phone, just select telephone in the audio pane and the dial-in information will be displayed. After logging on, your microphone will automatically be muted. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions pane of the control panel. You may send your questions at any time during the presentation. We will collect these and try to address as many questions as we can during the short Q&A session in the middle of the presentation and a longer one at the end. Today's presentation will be recorded and it will be viewable at baywork.org within the next 2 weeks. Again, I want to welcome you to this webinar, Integrating Ferrate into U.S. Water Treatment Practice. We're so glad to have our presenter, Dr. David Reckhow, with us today. Dr. Reckhow has been on the faculty of the University of Massachusetts since 1985 and is currently professor of civil and environmental engineering. His research interests include general aquatic chemistry, chemical oxidation of organic compounds in water, coagulation processes, removal of chemical pollutants in water, and aquatic organic matter in natural systems and drinking waters. Dr. Reckhow is director of a new EPA Drinking Water Center called the Water Innovation Network for Sustainable Small Systems and serves as principal investigator for half a dozen projects on natural organic matter, disinfection, by byproducts, and oxidation of organic contaminants in water. And now, with no further ado, I'd like to introduce you to and present Dr. David Reckhow, our presenter for today.
Great. Well, thank you very much, Robert. It's a pleasure to be able to talk to you all today. I think what I would want to do first is to just give you a minute or two of introduction, and then we can go to some of the polling questions. But what I will be talking about is this new and very exciting oxidant and disinfectant, ferrate, that most people in the water field haven't heard of. And it's been the subject of a lot of research, and we're hoping that we can bring it that last step and make it usable in real practice. My co-authors in all this are 4 students and my colleague, faculty member John Tobiasen, and I'll introduce you to them in just a few minutes. But as an introduction, I'd just like to say that this work that I'm going to talk about and in fact the work that we've done has been supported by the US EPA under a STAR grant and under our Small Systems Research Center called WINS. And so in this opening slide, you see the structure of ferrate in the lower right-hand corner. And it is based on iron. It's a highly oxidized form of iron. And if you go to the next slide, which you should see right now, you'll see a beaker full of a ferrate solution. And it's a deep red in color. Yet, in the bulleted points, we call it green because it really is very environmentally friendly. It does things that are good. It doesn't have some of the downsides of many disinfectants and oxidants. It is a powerful disinfectant, and it's very good at oxidizing disinfection byproduct precursors and doesn't produce its own hazardous disinfection byproducts. So with that as an introduction, I think this might be a good time, Robert, for us to go to the polling questions and just learn a little bit more about the audience before I go any further.
All right. We're going to show our first polling question here. And it is, in what capacity do you work with water? And there's 5 choices there: drinking water operations, wastewater operations, plant or pipeline engineering, plant or pipeline maintenance, or some other capacity. In what capacity do you work with water? I see the responses coming in. Great. All right. Okay, we'll give it a few more seconds and then we'll close the poll. Okay, closing the poll, and see some more answers coming. Okay. Okay, we'll close the poll in 5, 4, 3, 2, and 1. Closing the poll, and I'm going to share the results now.
So it looks like we're roughly split between drinking water operations and wastewater operations. That's great, although most of what I'm going to talk about pertains to drinking water, it could just as well in many cases pertain to wastewater. Ferrate has been proposed for wastewater application as well. So good, thank you. And Robert, should we maybe go to the second question now?
Sure, we'll do that. Our second question: how long have you been working in the water industry? Less than 2 years, 2 to 5 years, 5 to 10 years, 10 to 15 years, or over 15 years? How long have you been working in the water industry? I see answers coming in. Great. All right. Good. We'll wait a few more seconds here to give everyone a chance to respond. All right, we'll be closing the poll in 5, 4, 3, 2, and 1. And I'll share the results.
Okay, looks like we've got a lot of experienced folks. This is terrific. Most of you have been in the field for 10 years or more, although there are some that are a little newer, and so that's great. I think what I'll be presenting will probably be fairly new to most of you, although Ferrate has been around for many, many years, but it just hasn't been around in practice much. So let me go ahead, now that I know a little bit more about the audience, and tell you a bit more about the basics of Ferrate. And in so doing, I'm going to tell you what's good about it, maybe what isn't, and also give you a little bit of background on the chemistry and the effectiveness of Ferrate. First, I want to tell you about what happens when you add Ferrate to water. It's perhaps a little bit like ozone, if you're experienced with ozone, in that Ferrate decomposes in water on its own, even if there's nothing for it to react with. And what happens is, as you see at the top here, the chemical equation, it shows Ferrate, which is iron, once again in a very high oxidation state. It's the +6 oxidation state. Reacts with water and forms ferric hydroxide, which is a very common precipitate that we get when we add ferric coagulants and ferric salts. And a little bit of oxygen and hydroxide. And so what it essentially does is it precipitates as ferric hydroxide solids and oxidizes a little bit of the water to oxygen, but oxygen's great. There's no downside to this. So this is one of the reasons why we refer to Ferrate as a green oxidant. It can be produced on site, and there are various methodologies for that, but you can also produce it, of course, off-site and bring it in. So unlike ozone, which has to be produced on-site, you have the option of getting Ferrate from a chemical manufacturer, much like permanganate, perhaps, if you're familiar with working with permanganate. And it's produced by either an electrochemical method or a wet oxidation method. And you see one of the chemical equations here for how ferrate can be produced by mixing hypochlorite anion with ferric hydroxide and forming ferrate over here on the right-hand side. Now, ferrate has been proposed for a long time as a great oxidant and more recently as an effective disinfectant. There's a lot of work that's been done over the years, especially on ferrate's ability to oxidize contaminants and remove contaminants in water and wastewater. One of the great things about it is it won't produce regulated DBPs, at least very, very little in the way of regulated DBPs. And so it's a great alternative if you need some pre-oxidant and you're using chlorine. It's a great alternative to chlorine, and it also is a pretty interesting alternative, a low-cost alternative to ozone, we think. And it's considered a green oxidant. So a little bit more on the chemistry first before we jump into it. This is what we call a Pourbaix diagram. Some of you may have seen these before. And what we have here on this squared diagram is pH on the x-axis at the bottom, and the oxidation potential on the y-axis going up on the left or on the right, two different scales for it. And if you take a look at the center, you see a little hash-marked square. And this is essentially where most water systems operate. In the mid-pH range, maybe slightly alkaline, and in the mid-oxidation range, too. And so if you go up, you see FeOH4-2. That's ferrate. That's the chemical that we want to add. And that's at a much higher oxidation state than water typically is. And so when you add it to water, it wants to oxidize something so it becomes reduced. And it wants to go in this direction, heading down in this diagram. On the bottom, you see FeS way over here, and that is the iron metal that we have in pipes. So it's a solid zero-valent iron that in turn wants to, in this case, go up toward the zone where water treatment normally operates. And so there's a tendency for iron, of course, to corrode and form ferric and ferrous solids. And then just to fill out the whole list of different oxidation states, we have a little bit above the metallic iron, we have ferrous iron. Commonly the form found in slightly reduced groundwater. And then up here, ferric, and this is the form that we add as a coagulant, Fe+3. And so the ferrate is just another form of iron that wants to become ferric, and so it precipitates as ferric hydroxide in water. Now, there's one other element to all this too, and that is the pH behavior. And so as you go from neutral pH to higher pHs, the ferrate tends to lose hydrogen ions, and it ultimately becomes just FeO4-2, the highest charge, negative charge form. And as you go below pH 7, it tends to form HFeO4-, slightly less charged and more protons. And so for this reason, because water treatment can operate on both sides of this divide here, the pH is very important in how this operates. Okay, so this is the background chemistry. We've known this for a long time. We've been also studying ferrate and have known its benefits for a long time. So we asked this question to ourselves when we first started working on ferrate at University of Massachusetts. Why isn't it used in U.S. water treatment then, if it's such a great chemical? And we came up with several reasons why, are really factors that need to be addressed in order to implement its use in water treatment. And probably the single most important is that the U.S. EPA has not evaluated ferrate yet for disinfection credit. And so in other words, it doesn't have a set of CT tables that you can use to get credit for it. And so you still, even if you use ferrate, and even though it's a good disinfectant, you still need a conventional disinfectant to meet regulations. In that regard, EPA is starting to look at and has been working with us to develop design parameters for developing a CT table. And so that may change in the next few years. Number two is it's got to be cost competitive. And so to be cost competitive, it means that it's easy to add, it's low cost to buy, and there aren't other hidden costs. And we believe it is fairly inexpensive, a much less expensive option than, let's say, ozone. It also should not interfere with other treatments used in the plant. You don't want it messing things up in the plant for you. And then it would be great if it offered some additional advantages over existing treatments, such as better removal of trace contaminants in water, better control of organic and inorganic disinfection byproducts, lower energy consumption, lower carbon footprint, easy to use, reliable, and then all the better if it could improve the aesthetics of water. These are all things that we look to as supplemental benefits above and beyond any disinfection we might have. And so to answer these questions, we believe that it does meet all of these criteria. And the only thing we're waiting for at this point is the CT evaluation by EPA. But let me try to convince you a little bit of some of the benefits that I mentioned. Now, just so that you don't think we know all the answers or we have all the answers to ferrate, one thing that we don't quite know is exactly how ferrate decomposes. We have some good ideas, but there are a few key elements in this that we haven't quite understood. But to be fair, I have to say that we don't entirely understand all the steps in the decomposition of ozone or chloramines too. So the ferrate is not alone in this regard. However, one of the things that we don't understand exactly is to what extent does ferrate in the +6 oxidation state go through the intermediate oxidation states on its way to +3, and the intermediate ones being +5 and +4. And that's an important feature because these intermediate forms could be pretty reactive. Okay, so now let me introduce you to our group. And that's me on the upper left and my colleague John Tobiasen in the upper right. We have in the center our two PhD students who have recently finished, in fact, Yanjun Jiang and Joe Goodwell. And on the bottom are two master's students who are still in progress, Josh Cunningham and Xuan Mai. And most of what I'm going to present today is going to be the work of Yanjun Jiang, so I want her to have proper recognition in all this. All right, so let me move ahead and tell you a bit more about where we're going and some of the important elements of the chemistry and the process engineering. First, just to remind you that ferrate, we know, decomposes from the +6 oxidation state down to the +3 ultimately, and in so doing, to go from 6 to 3, it's got to lose pick up 3 electrons, and it can pick them up in one electron at a time, or it can pick them up in different stages, 1 electron then 2, or 2 electrons then 1, and this leads to different types of intermediates. And one of the questions that we've often asked, and we need to establish a little bit when it comes to determining disinfection credits, is how important are these intermediates, the iron 5 and the iron 4? But that's a little more really for the chemists and the researchers. But I wanted you to know that that is one of the areas of active research right now. Okay, so a related issue is raised by this question. Does ferrate decay? And we know it decays in water, but does it decay the same way for all types of waters? Is the mechanism the same? Does it decay at the same rate? Can we predict how well it's going to decay? And this is important for understanding how we can relate laboratory studies at laboratory scale to actual full-scale water treatment plants. So here's a little glimpse of what it looks like to do these studies in the laboratory. This is some data that we generated at UMass, and what I'm showing is the loss of residual ferrate over time. And so if you look at this top line with the open red circles, this is when we do this, and we add this is 50 micromolar, which is a couple of milligrams per liter as iron of ferrate, typical dose that you might use, to a water that has no organic matter in it. And so we were trying to make this very simple, and we buffered it with phosphate because pH is important, and you get a decomposition that looks like this. And after half an hour, you have lost maybe 2/3 of the ferrate. That's fairly typical. What is surprising in all this, and I'm going to explain it in a minute, is if you instead use a different compound to control the pH, in this case borate, the decomposition is much faster. And we were puzzled by this, and so the presence of phosphate seems to stabilize and make the ferrate last longer. Okay, this is important because, like any disinfectant, you want the disinfectant, the residual, to last as long as possible to get the most effective disinfection. So you've got the longest exposure of the disinfectant to microorganisms. Okay, so let's see if I can go to the next slide. Sorry, okay, here we go. So here's a little bit about how the chemists explain all this, and I apologize, and this I'll show you a couple of figures like this and then we'll get rid of the chemistry. But for those of you who are interested in what's happening, the ferrate that we add to water is down here. It's the red box, Fe+6. Does some unusual things chemically. It forms what we call dimers, the start of a polymerization. And those dimers react in water, giving off a little bit of hydrogen peroxide. Ultimately, it forms this intermediate oxidation state, Fe+4, and eventually it may go to Fe+2 and Fe+3. But the final resting place for ferrate is Fe+3 under normal water conditions. Now, without anything else in the water to interfere with, that Fe+3 would precipitate as a ferric hydroxide precipitate. So for those of you who are familiar with use of ferric salts as coagulants, you know this is what you get. Well, what we've learned is that precipitate will react with the residual ferrate and give rise to other reduced compounds. And what it really does is it accelerates this decomposition, shown by this heavy blue arrow over here. It also produces some other oxidants in the process. If, however, you have a compound like phosphate present that can bind the Fe+3 and form a hydroxyl phosphate complex, you prevent the precipitation of ferric hydroxide, and the iron, the ferrate iron, is far more stable because it can no longer decompose. So you're looking at the difference between this diagram and this one. So without phosphate present, this is what happens, and it decomposes quickly. With phosphate, it's much slower. Okay, so another feature of all this is the presence of organic carbon and other oxidant demands. And what this figure shows is not ferrate, but it just shows a typical oxidant like chlorine, and what normally happens when you add chlorine to water. Chlorine will also be lost with time, and it's usually because it's reacting with organic matter or some other substance in the water, not just simply auto-decay, which is what ferrate does. And if you add, if you've got a water that has very little organic carbon, you may get a profile like this upper red line over time. And if you've got a little more organic carbon, you'll get a lower profile like the gray, and finally at a higher organic carbon level, you'll get the blue. So as you go down, you're having less and less chlorine, faster decay of chlorine due to the presence of higher levels of organic matter in the water. Well, with ferrate, it's surprisingly the exact opposite. Here's an example of ferrate residuals over time, and this bottom line now is the water that has no organic matter in it at all. This is deionized water with a borate buffer. Ferrate goes away most quickly in the absence of organic matter, and as you have more organic matter present, it can go away more slowly. It can stabilize it. And this is surprising. We didn't understand it when we first saw it, but now I think we do. But it's also a really great feature too, because what that means is you don't have to be so concerned about high levels of organic carbon causing a rapid depletion of the oxidant or disinfectant. This is what happens with traditional disinfectants like ozone, chlorine dioxide, and chlorine, but not with ferrate. And the understanding is that what ferrate does is it coats that precipitate that you normally get what dissolved organic carbon does is it coats that precipitate you normally get from the precipitation of ferrate, it's the ferric hydroxide precipitate, and really prevents the remaining ferrate in solution from reacting with it. And so it forms a protective coating around this and slows down the decomposition, which is a really good thing. Whereas without the natural organic matter, you get fast decomposition. So this is a nice feature of ferrate that we didn't predict ahead of time. All right, one more thing, and I want to stop for questions. I also want to say a little bit about that precipitate. It's not exactly the same as what you would get with ferric chloride or ferric sulfate coagulants. It's close. It's from the standpoint of its chemical formula, it's about the same, but its morphology and its sizes are different. And so with ferrate, you get these compact crystalline, more crystalline structures you see on the right. This is an electron chromatogram, microgram rather. And with ferric coagulants, you get these larger open structures that are less crystalline. And if you look at the size fractionation, you see ferrate will give you smaller particles as compared to the ferric coagulant that we might add. Okay, so that is pretty much the background I wanted to give you. And so now I thought this would be a good time to open it up for a few questions and see if there's anything you'd like to ask at this point.
Well, Dr. Reckhow, I think we have two things present here. You did an excellent job of presenting this, and we must have a very intelligent audience because there are no questions at this time.
Okay, all right. Well, okay, so please then make sure you remember your questions over the second half of the webinar, and I'm happy to answer anything you've got at that point. Okay, so now let's go a little more away from the background information now that you have a little bit of an understanding of what happens when you add ferrate to drinking water. We're going to talk about what it does that are good, the things that are good that we like. And number one is we know ferrate reacts with what we call micropollutants or trace organic and inorganic contaminants in water. And it oxidizes them and removes them in the way that we want it to. And the amount to which you get oxidation of these pollutants in water is going to depend on the exposure, which is maybe quantified by this in the same way we quantify disinfection through concentration times time product, a CT. And that tells you how long the contaminant that you want to remove has been exposed to ferrate and to how high a concentration it's been exposed. And as CT goes up, of course, you get more complete removal. The rate constants for micropollutants with ferrate have been studied and are in the literature, and we've got a lot, maybe 30 years of work that's been done on this. However, one of the complicating features is that you can use the theory, and it's great, but it might not always work perfectly. And so it's always good to check. Anyways, and then the reason is that you have not just ferrate present, but you have some of these intermediates, the iron 5 and the iron 4, and ROS stands for reactive oxidant species, things like hydrogen peroxide that can form as well. All right, well, so you can go into the literature and find papers like this, and one of the most prominent researchers in this area is Virendra Sharma, who's now at Texas A&M, and he has published a couple hundred papers on ferrate and has summarized some of the information that we have to date on its reactivity with contaminants. And you can see from this list that there's a whole group of organic and in another paper inorganic substances that ferrate can react with. And so that's great. In order to make use of this information and to predict how effective ferrate is going to be, you have to determine what the CT is, not just for the purposes of disinfection, but also for the purposes, I say, of understanding its ability to oxidize or chemical contaminants in water. So what I have here are some of these same concentration profiles for a number of different waters that we've studied over the years. And these tend to be, except for Houston, Texas, these are all and New York City also. Most of those systems we worked with are smaller systems. And what you see is always a degradation with time that starts out fast and slows down. And the degree to which you get the loss of ferrate seems to be almost in reverse order to the total organic carbon concentration. But regardless of which type of water you're treating, after about an hour over here, you're pretty much have lost all the ferrate. And so what's most important is that CT product, which is essentially the area under the concentration versus time curve. So we can do that. We can calculate what that area is under each one of these 7 curves. And what I show in the next figure is those areas, those CTs, for each one of these now 6 different communities. And it was evaluated for 2 different dose levels and 2 different pHs. And you see the CTs range from a value of maybe 3 all the way up to a value of as high as maybe 65 or 70. Now, the key here is, first of all, looking at the effectiveness of disinfection. If you look at the right over here, I've got a line for 2-log inactivation of Giardia and a line for 2-log inactivation of cholera viruses. And what you see here is a measure of how effective ferrate is going to be in each one of these waters, suggesting that for Giardia, you're going to be able to achieve 2-log removal in at least 5 out of the 6 waters if you go to a higher dose and a higher pH. And for cholera, you'll get essentially, you could get 2-log inactivation for all of the waters as long as you're picking the dose and pH correctly. And so this is great news, and this is once again preliminary data that we hope to fill out and get more information on as the EPA develops its CT curves. But this is an example of how effective ferrate is as a disinfectant. By the way, these doses that I'm talking about, 25 and 50 micromolar, are just a few milligrams per liter as iron, typical doses you might use in water treatment. Okay, in addition, we've got a lot of rate constants for the reaction of ferrate with a whole group of contaminants. Arsenic, for example, azide, sulfur, reduced sulfur compounds, etc. So these rate constants in themselves are not all that helpful unless we can combine that with the other information we have and predict removal rates or degrees of removal. And this is what we did. This happens to be for one of the waters. We picked one of the large systems we worked with, Houston, Texas. And in this particular case, a higher dose, a couple of milligrams per liter, or 15 micromolar dose of ferrate. And what this shows is that there are some substances that are essentially untouched by ferrate, much like what happens with ozone. Ozone is selective and only oxidizes certain types of contaminants. And a good example would be the simple alcohols, for example. However, there are substances way down over here that show 0 fraction remaining or 100% removal. And these are reduced substances like sulfides, for example. And then there are a wide range of substances that are in between that have pH-dependent behavior on that determine the percent removal. And so in this particular case, this is one of the pharmaceuticals, sulfamethoxazole, which shows about 50% removal at pH 7.4 or 7.5, and maybe 90% removal down low at pH 6, and not as much at higher pH. And so this gives you an idea that, well, ferrate won't, like most oxidants, remove everything, but it is selective and it will oxidize an awful lot of substances. And here's a similar set of calculations based on a lower dose, still removing entirely some of these substances like sulfides, not touching the really recalcitrant compounds like alcohols, and I would put the fluorinated compounds up there as well. But the pharmaceuticals, personal care products, are going to be partially, if not completely, removed in some cases. Okay, another area of importance is the disinfection byproduct precursors. Again, drawing the analogy with ozone, we can compare what ozone does to DBP precursors, in this case trihalomethane precursors, with what ferrate does to trihalomethane precursors. And you see is a surprising, a remarkable similarity, in fact. And so looking over at the ferrate data on the right, we've got concentrations from many different water utilities, and I don't have the full set of symbols, the key up here, but we've got about a dozen or so different types of waters from different locations. And what we see is at doses that are fairly typical, that may be about 0.6 or 0.7 milligrams of iron per milligram carbon. So what that means is if you've got a 2 milligram per liter DOC, you'd be adding about maybe 1.3 milligrams per liter of ferrate. And we get about 20-30% destruction of THM precursors. And that's in fact very similar to what we see with ozone too. And so we think that they behave quite similarly. So how does this all fit in? And I could go on and on, but there isn't enough time to go into all of the different features and what we've learned from ferrate. So I want to finish off with a little bit of a discussion of how it fits into typical water treatment. And so we're thinking of at least a couple of scenarios here. Number one, if we're talking about groundwater, it's very likely we would be adding ferrate as a pre-oxidant prior to any treatment. You'd want to have probably some way of either sequestering or removing the iron solids. That could be done perhaps through, aside from sequestration, possibly a pressure filter. And so for groundwaters, this is typically probably what we would be looking at. For surface waters, we might consider adding ferrate at one of two locations. One is a pre-oxidant ahead of conventional, as shown here, conventional treatment, so that you have the ability to add a coagulant afterwards. Now many people ask, well, ferrate is an iron solid, or an iron salt rather, and it forms ferric hydroxide solids, and so do you need to add a coagulant after adding ferrate? And the answer is typically you probably would want to, because you're not adding as nearly as much ferrate as you would typically add an iron coagulant, iron salt like ferric chloride or ferric sulfate. So you probably want to add a little more, but the ferrate solids, the hydroxide solids that form from the addition of ferrate will help you with coagulation and essentially serve as an in situ coagulant. Anyways, you would probably want to add it as a pre-treatment in one option. Then through flocculation and settling, gravity settling, or maybe dissolved air flotation, you can remove the solids, and you know, a granular media filter, maybe a roughing filter too, would help to polish the water, certainly. Then the other alternative is to add it as an intermediate oxidant. After initially removing the easily coagulated organic matter and particles through, let's say again, a conventional treatment, and then treating that clarified water, either from gravity settling or dissolved air flotation, with ferrate before going on through a filter. You probably would want some sort of a filter afterwards, again because you are producing a small amount of solids and you'd like to remove that if you could. And so we've looked at both of these scenarios and asked the question, how well does ferrate work in these two scenarios? And one important issue is how well does it control the disinfection byproducts? Because as I go back to this previous slide, you're always going to want, even though ferrate is a disinfectant, it doesn't maintain a long-term residual. It won't maintain a residual in a distribution system. So you're always going to want to add some chlorine or chloramines at the end, maybe chlorine dioxide at the very end to maintain a residual throughout the distribution system. So you'll always have the possibility of forming chlorinated disinfection byproducts. And so we want to look at the impact of ferrate on these precursors. Well, I already showed you some data on what ferrate does to precursors when added to a raw water. And here's an example, some more data of that sort on the upper left-hand corner. But what we hadn't had a chance to do until now, until we started looking at intermediate ferrate, was to examine what happens after you coagulate first. You measure the precursors left after coagulation and clarification, then you add ferrate again, or you add it as an intermediate, and measure how much is left. And in this case, we find that we get a higher level of destruction of precursors. Even though we've already removed quite a bit, we're seeing, instead of, let's say, an average of 20 to 25% precursor removal at intermediate doses, we're seeing something more like 40 to 50% removal of THM precursors. And we see this also for the haloacetic acids. And so this is exciting because it means that when you're adding ferrate, going to the previous slide, as an intermediate, it's especially effective in controlling this disinfection byproduct problem. Now, one of the questions you might ask is, okay, that's well and good, but what does ferrate do to the performance of a granular media filter? And we've been looking at this also in laboratory scale, continuous flow pilot, and a continuous flow laboratory scale pilot. And what we see is much like what we see with ozone, in that it doesn't seem to create any additional head loss buildup. It doesn't cause a deterioration in granular media filtration in any way, even though you are producing some solids. Interestingly, the solids aren't of the type that caused the filter head loss buildup. But what it does do, and this is also somewhat in parallel with ozone, is it sometimes can improve the performance. Not only does it not cause a deterioration in the performance, but it can improve it so that you can get sometimes slightly longer filter runs, depending on how you define the filter run, whether it's based on head loss buildup or filtered water turbidities, or lower filtered water turbidities too. And certainly what it does is it gives you lower filtered water UV absorbance and precursor levels. And so that's all a really positive thing, and we're excited about that. Okay. Here's another figure. This just shows the haloacetic acids. This happens to be the trihaloacetic acids, and showing the fractional removal in pre-ferrate application, pre-treatment application of maybe, what does that look like, about 30% maybe, or 25%. But then when you get to intermediate ferrate, the percent removal can increase up to 60%, let's say. And so we're definitely much more excited about the application of ferrate as an intermediate. But it still has benefits if you do need a pre-oxidant early on in treatment as a pre-treatment as well. Okay, so I'm going to stop my presentation of data here and just go over some conclusions and what we've learned so far. First is that ferrate decomposition is substantially more complicated than we first thought. Even though we've been studying ferrate in the laboratory for 30 years, once we start looking at real waters and understanding how the real waters differ from laboratory prepared waters, we recognize that there's this issue of precipitation of solids that accelerates the decay. And that can be good or bad, but one of the good features is that natural organic matter slows it down. And so as a result, you don't get this rapid loss of oxidant with highly colored waters that you do with other types of oxidants. You don't see it as much with ferrate. A downside is that there is a tiny amount of oxidation of bromide that can occur, but far less than you would get with an oxidant like ozone, let's say. And there are substances that can suppress the decomposition and oxidation, decomposition of ferrate and the oxidation of bromide. Phosphate is one, but there certainly are other anions in natural waters that can do that too to some extent. Ferrate is capable of oxidizing regulated DBP precursors. So in other words, the trihalomethane precursors and the haloacetic acid precursors. And the effectiveness is similar to what we've observed for ozone. And so I would say that at mass doses, the same mass dose, if you want to compare it in that fashion, you need maybe just a little more in terms of mass, 1 to 2 times than you would for ozone to get the same impact. But of course, ozone is a whole lot more expensive, and so adding 1 to 2 times as much ferrate is going to be cheaper. Bromine incorporation does occur, and you do get a little bit of formation of brominated byproducts when you have ferrate, but it's far less with ferrate than it is with ozone. You do get a tiny amount of bromate formation, but we have yet to see a water where that is significant so that the bromate ever exceeds the MCL of 10 micrograms per liter. So it seems that bromate is not an issue, although it is for ozone. We're still learning about the exact nature of the effective iron. We know clearly the ferrate that we add, Fe plus 6, is very effective, but it may be that some of these intermediates are effective too, and that can be important in understanding how ferrate behaves a little differently in one water than another. A few other conclusions. When you introduce ferrate as an intermediate, as I showed, it seems to be much more effective at destroying disinfection byproduct precursors as compared to addition as a preoxidant. Our early data show that ferrate can be very effective at inactivating bacteria, viruses, and protozoans, as I showed some of the CT data, although we are waiting on the EPA to finish design and launch a CT study so that we'll get firm numbers for CT tables. Ferrate is also, in a preoxidant mode, does not seem to adversely affect filter performance. This is important and something that really needs to be addressed a little more than we have already, but the indications so far are pretty good, that it's a lot like ozone and it can often improve filter performance when added as a preoxidant. And then it seems to be especially interesting as an alternative for small systems that have water quality challenges, because it is a powerful disinfectant or oxidant and disinfectant like ozone, but it doesn't suffer from some of the same complications, the need for some complicated equipment and operation that you often run into with ozone. And so if you want to learn more, I'm very happy to tell you a little bit more. We also have a website right here that features some of the publications from our research as well as some other information, and I welcome you to visit that website. In closing, I would just like to once again acknowledge the EPA and their support of our Small Systems Center, the EPA STAR program, and our co-authors, my co-authors, as well as others at UMass who have helped, and in particular the personnel from some of the participating utilities. Most of the small utilities we've worked with have been in the Northeast region, but we've gone outside the Northeast U.S. as well, and there are many folks who have helped us in this regard. And also, I'd like to thank Battelle for providing the ferrate in this project that we've used. So, let me just stop and at this point bring it to a conclusion, and I'm very happy to address any questions you might have on this. Thank you.
Well, thank you, Dr. Reckhow. We do have a few questions now. The first one I'm going to read, you may have answered, this question may have come in before you provided an answer, but I'll read it anyway. The question is, and this is brought in by Brad, we use chlorine dioxide as a primary oxidant. Would ferrate be considered a replacement for chlorine dioxide, or would there be an advantage in using it in conjunction with chlorine dioxide?
Well, my perspective is that it could be used as a replacement for chlorine dioxide. Now, having said that, there may be some synergistic advantages to using both. We haven't looked at this issue, and so I have to admit that we don't really know. But our preconceived notion is that it could be used as a replacement for a strong preoxidant like chlorine dioxide.
Okay, thanks. Here's a couple more questions from Todd. Is it accepted at this point to use ferrate in addition to a standard disinfectant such as hypochlorite, same as question before? For example, if we were to add a small precoagulant ferrate dose to help control algae growth in our water treatment plant?
Yes, absolutely. Indications to this point are that ferrates can help control algal growth, and that is in fact the scenario. One of the scenarios that we have envisioned and embraced is the use of ferrate as a preoxidant when you do need a preoxidant in your treatment plant for whatever purpose, and controlling growth is a good reason to use a preoxidant.
Okay. And here's another question. How is it added at a treatment plant? As a powder? Does it need to be mixed on site? We are familiar with the use of powderized permanganate.
Yes, so that's something that is still being developed, but we imagine that it could be done both ways. One could certainly use it as a granular material, create a day tank, and you have to be careful about making sure that it's stabilized in the day tank. It won't last for days at a time, but there are ways of helping to stabilize it. And so that's the way I envision it, with a feed pump, a chemical feed pump from a day tank, probably is the most likely scenario.
Okay, thank you. I have a question for you, Dr. Reckhow. The EPA, is there an anticipated time, or is there any planning on when they might be investigating this a little further?
Yeah, it's a really good question. Well, about 5 or 6 months ago, we were all set to do the preliminary study for the CT research that needs to be done, and so this is a two-step process. EPA was going to contract with us to do a study design, and then they would probably actually implement the study and devote some of their own internal resources. Now with the change in administration, a lot of this is on hold, and so we don't know where it's going to go. So we thought 6 or 8 months ago it was going to move along very quickly, but now we're not so sure. Ask me that question again in another 6 months, and maybe I'll be able to give you a better answer.
All right, that's good. I have a few more questions for you. How stable is the solution, and what is the shelf life?
Yeah, so the chemical itself, if you keep it dry, the dry chemical, has a shelf life of, in our experience, a year or more. So that's, it does last a long time, but you do need to make sure that it's kept reasonably dry. In a solution, it will decay, as I showed, and so we're anticipating that with the use of stabilizers, you'll be able to keep it for a day without losing too much of its strength, but you don't want to go any further than that.
Okay. Another question. Did you say there was an alternative to generating it on site?
Yes, there is. There's one that's commercially available that has been used, as far as I know, only on wastewater to date, not on potable water, and that's an alkaline high pH chlorine reaction, and so that's, the exact method and conditions are proprietary, but there is a company that does offer this. And then there are, in research realm, electrochemical methods that are not ready quite yet for prime time for use in a treatment plant, but I imagine that we're going to see this happen. One of the major producers of off-site ferrate is Battelle. They have a patent on its electrochemical production, which is a very efficient one. And they tell me that they're prepared to go into high-level, full-scale operation as soon as they believe that the market is there, and I think the market will be there as soon as the US EPA can establish the CT tables.
Okay. A few more questions here, a couple more questions. Any research on use in wastewater, for instance, instead of hypochlorite?
Yes, there is. I don't think there's been quite as much. And ironically, that is the one area where Ferrate has been applied at full scale in wastewater. And so it looks interesting, and it does, because it does dissipate. It's an interesting oxidant. It's a strong oxidant, but it dissipates much more quickly than chlorine does. And so the feeling is that it can achieve very good disinfection of the wastewater, oxidize problematic substances, and with a reasonably short holding time, it will be essentially gone too.
All right. Another question. Have you or others looked into Ferrate's effectiveness at removing cyanotoxins?
Ah, very good question. That's on our list of things to do as part of our Ferrate project, and so that's one of the next things. We haven't yet, but knowing a little bit about the chemistry of Ferrate, I suspect that it's going to be effective with some, a little bit like ozone and maybe to some extent chlorine, and not as effective with others. There are some that are mostly hydrocarbon in nature that are very recalcitrant. So I think we're going to see, I'm just predicting now, of course, a mixed situation where it's good for some and not good for others.
Okay. This question I think you answered somewhere in the presentation, but I'll ask it. It won't hurt to review it. Could you add Ferrate as both a pre-treatment dose for algae and also as an intermediate for DBPs?
Yes, yes. If you do need to apply a pre-oxidant, I think that's a great scenario because you can still meet the needs of the pre-oxidant with Ferrate without having to add chlorine that can be problematic. And you can get the biggest bang for your buck, too, at the same time by adding a little more, or maybe the bulk of it, as an intermediate oxidant. If you do have two places where you can add an oxidant, I think that's a great approach.
All right. And another question. You touched on PHCP. Can Ferrate be considered a replacement to advanced oxidation for PSCHs and EDCs?
Yes, absolutely. It is a powerful oxidant. It doesn't react identically with ozone. In other words, there are some substances that ozone reacts more quickly with. On the other hand, there are some substances that Ferrate will do a better job with, largely because it tends to persist a little longer than ozone. And so it's going to be similar but not identical, and it is an alternative for the pharmaceuticals, personal care products, and other trace organics.
All right. Well, this has been a fabulous webinar, and thank you, Dr. Reckhow. Some of you may have some more questions. I don't see any in the queue right now, but it is time for us to end our webinar. I want to thank Dr. Reckhow for presenting such a great information and sharing his vast knowledge with us. And I want to thank all of you for joining us today. The recording of this workshop, this webinar, will be posted at baywork.org within the next 2 weeks. Also, we will email contact our certificates to those who answered yes to the questions regarding them on the registration form. Lastly, we really want to know your thoughts about this webinar. Please take a moment to complete the survey you will receive immediately after we are done. It is only 3 questions. Do you have any final words, Dr. Reckhow?
No, just that I hope you will all keep your eyes open and be aware as the time comes when we are at a point where we can actually start using Ferrate, and I think it's going to find a nice home. It's going to find a good niche in water treatment in the U.S.
All right, great. Well, we appreciate you doing this today. And on the behalf of BAYWORK, thanks again, everyone, for joining us. Have a great rest of the day and the rest of the week. Goodbye, everyone.